Good day everyone, and I'm feeling very honored to present you our current research with the title Integration of the Advantage Actor Critic Algorithm for Production Scheduling in a Two-Stage Hybrid Flowshop Environment. My name is Falk Gerpott, and I'm a graduate from the Otto von Guericke University in Magdeburg and the Chiang Mai University in Thailand. Today I would like to give you a short introduction about our current research. I'll define the aims of our work. I'll show you the research objective and the tools that we're using. To illustrate you the aim of our work, we created an example company that is currently investigating its nowadays and future challenges and how they can react to this. First of all, there's the demand for fast production and delivery that they need to fulfill. There's an increasing product diversity and shorter product life cycles. As we can see from the current pandemic, there are unexpected changes happening along the whole supply chain that the company needs to react on. Especially in the future, there might be a problem in certain areas with skilled labor shortage. We're living in a globalized world where we have a worldwide competition, which is constantly putting cost pressure on the company. On the other side, we have the chances for new technologies and improving computing power that can be used. All in all, they can see that there is a need for good quality real-time decisions based on changing circumstances. This need might occur along the whole supply chain, but in our research, we're focusing on the production stage. And in terms of the different areas of planning, we're applying this to the scheduling. And as an example production system, we're using a two-stage hybrid flow shop of a company which is producing printed circuit boards. And they have on the first production stage a group of 4 machines which are surface mount device machines with sequence-dependent setup times and job-specific process times. On the second production stage, we have 5 automated optical inspection machines that are used. And for the company, the target criteria are the make span as well as the total tardiness of all the jobs. For the scheduling, so the allocation of jobs to certain resources, as well as determining the order of the jobs, we have several approaches available. There are the EXF methods, or the approximation methods, which are heuristics like simple dispatching rules, or meta-heuristics like genetic algorithms, or even hyper-heuristics. But these traditional approaches always have a trade-off between high computational effort and the solution quality. We can choose, okay, we want probably very good results in terms of scheduling, but they might calculate for a quite long time. As well, when we have certain changes in the production system, like breakdowns or other things occurring, we have a low flexibility and adaptivity that we can react on and need to calculate for a long time again. That's why we come up with a machine learning approach, reinforcement learning, where we have an environment and we are transferring some information, the so-called stage, to an agent, and this agent decides based on this information what action it will perform. And the environment is rewarding this action with a reward. And in terms of the algorithm that we're using, the Advantage Actor Critic, short A2C, we're not just interacting with one environment, we're interacting with several environments and collecting this information. For representing our agent, we are also using deep neural networks. And there's not only an actor interacting with the environment, but also a so-called critic who is supervising this learning behavior. Based on this information, we developed a procedure model of applying reinforcement learning in production systems. And therefore, we perform a system analysis of our physical system, and to transform this into a model, we need to define certain assumptions, as well as the objectives that we want to do with this optimization problem. And in our case, we will develop a conceptual model where we have a deep reinforcement learning algorithm that is using deep neural networks, which is interacting with a discrete event simulation model. And in practical terms, this is done with the open source framework and free framework Stable Baselines 3, which provide the deep reinforcement learning part, and Salabim as a library for discrete event simulation. we will show you some numerical results. So we perform some experiments with the training data that we have, and in future publications we will also apply this to our test data and then compare the performance to certain benchmarks like heuristics or meta-heuristics to then, in the future vision, apply these agents back in the physical system. So how is this conceptual model looking like in our case? We have a production system where, for example, one machine requests a job, and then we're passing certain information about the machine status and about the jobs to the state extractor, and the state extractor is forwarding these information to our actor critic system. And our actor critic system is deciding for certain dispatching rules. And then this job will be selected according to this dispatching rule. We will also check if the other machines already have setups for the selected job family, because there's kind of a restriction that only one job family can be set up on one machine. And in case this is false, we will calculate the reward, which is required for reinforcement learning, and then transfer the job to the machine. Let's look a little bit more into the details. What information are we actually passing to our agent system? And as I mentioned, therefore we're using the state extractor, which is calculating certain statistical values like the minimum, the maximum, the average, the standard deviation, and the number of features of certain categories. And these categories can be job specific, like for example we're checking the buffer and calculating the tardiness, the earliness, or the different process times on the certain machines, and calculating the different values and passing these values to our agent. And this can be job specific values, like I mentioned before, but also machine-specific values like the same setup process time, comparing the setup of the different machines and the corresponding jobs in the buffer, or workloads of the different machines that are currently running at the moment, to provide a wide information to the agent about the current system status and the job buffer situation. On the other side, we're providing different dispatching rules to the agent that the agent can choose between, and keeping in mind that our target criteria is the make span as well as the total tardiness. We provide different dispatching rules which are addressing this kind of target criteria. So we have due date based dispatching rules like the earliest due date or the least slack time that the agent can choose, or we have cycle time based dispatching rules like the shortest process time, the longest process time, or even the shortest setup time, and then combine this with another dispatching rule to provide different options to our agent that the agent can choose between. In addition, the reward design for reinforcement learning approaches is very important, and as I've mentioned before, there are certain target criteria that we have. This is on the one side the tardiness, and on the other side the make span. So how do we reward our agent with a target criteria which is calculated in the end, for example the tardiness in the end when the job leaves the system, but we need to give a reward at the point of decision, which we have seen in our conceptual model is when the machine requests a job. Therefore we can see a problem. So we know the setup time, we know the production time on the SMD machine, and we don't know the weighting of the job on the second stage because this might be depending on other agent decisions, and then we know again the setup time and the process time on the second production stage. So we need to give a reward and the point of decision, which is depending on the point of competition. So we can only approximate the remaining time in the system that we want to use as a reward to calculate the tardiness. And therefore, we introduce the so-called arrival value, which will approximate the tardiness or the earliness of the job. And since we're only making a decision on the first production stage, we want to use a proportionate value. So we take the proportionate slack time and subtract it from the time that are used on the first production stage, which is the setup time and the process time, as we can see in the green boxes above as well. And then we can kind of estimate if our job will be early or delayed. And then we're transforming this arrival value and comparing it to the maximum possible value, like the compared to the maximum possible tardiness or earliness, and we can see the best results when we're not only punishing the late arrivals but also the early arrivals to kind of keep a balanced tardiness level. On the make span side, we want to have a balanced capacity utilization, and therefore we're calculating the different process time of the last 5 selected jobs and compare this with the average process time. And again, to divide this in a value range between 0 and -10, we compare this to the maximum possible discrepancy that this value can have. And then, since we have 2 target criteria, we combine this in the total reward and weight it with a 50-50 weighting, which is of course depending on the user's preference. Coming to the practical implementation, how does this look in practical terms? We can see that we want to simulate a system behavior of our production system, like the setup of machines, the process of machines, the weighting in the buffers, and so on. And on the other side, we need to make decisions for certain dispatching rules. And the system behavior is simulated with a Python-based Salabim simulation model, and the decision making is done by a deep reinforcement learning agent from the Stable Baselines library, which provides several deep reinforcement learning agents that can be used together with certain environments. And these system and decision-making tools need to communicate with each other, and therefore we use the OpenAI GIM interface, and this allows certain customized environments to communicate with our agent model. And this OpenAI GIM interface has specific requirements, for example, the reset method. And as we've seen in the conceptual model, we are running our discrete event simulation model until the first sequencing is required. And in this case, we pass on the state information, as we have seen from the state extractor, to our agent, and our agent is deciding for an action, which is a certain dispatching rule. This dispatching rule is passed to the so-called step method of the OpenAI GIM interface, and then executed in the simulation model until the next machine becomes idle, and we're passing a new state as well as the reward of the previous action as well as the done flag back to the agent, and this loop is repeated until our simulation model tells that the done flag is true. To train our agent, we are performing different production cycles, so performing a complete schedule of a production and repeating this. And we can see on the top left with the make span that our make span is slightly decreasing over time, so our agent is learning to minimize the make span, as well as underneath the total tardiness. While we have in the beginning a quite high total tardiness, we can bring it down close to 0 in the end, and this is also represented in our cycle reward that we are receiving. On the top right, we can see the different dispatching rules, that our agent is mixing different dispatching rules based on the observations that they receive. We can see that the number of jobs which are early is increasing and the number of delayed jobs is decreasing, which is what we want to see, as well as a special behavior of the maximum earliness of jobs, which is also decreasing, so which we intended with our reward. We have a kind of a more balanced situation. To give you a short outlook, we're coming back to our procedure model. We want to address future challenges on the model level, like testing the test datasets, not only the training datasets, and compare them to benchmarks like other heuristics or meta-heuristics. We want to test different rewards as well as other deep reinforcement learning algorithms which are provided by the Stable Baselines library, and then perform hyperparameter studies. On a transfer level, we can think about multi-agent systems, where we're not only performing decisions on the first production stage, but probably also on the second production stage. We can simulate dynamic system behavior with feeding in new jobs into the system and test it with more diverse and larger data sets. On a meta level, we will further investigate the problem with having an immediate reward with future target criteria, where are the limitations for this, how to perform systematic hyperparameter studies, and probably we can understand state-specific dispatching rules decisions by our agent back to our physical system. So thank you very much for your attention, and I'm looking forward to a discussion right now.